Good afternoon. We will begin the afternoon session. And we have as our first speaker, Professor Varun Bhalerao from IIT Bombay. He's going to talk about electromagnetic counterparts to gravitational wave sources. Varun, you will have 50 minutes and 50, and then we'll have 10 minutes discussion. Is that all right?
Sounds good.
Great. Please take it away. Thanks.
Thank you. Hi everyone, and sorry I'm not there in person. I was a bit unwell. I'm doing better now, but unfortunately still a bit weak, so couldn't have been traveling there. I'm going to talk to you today about electromagnetic counterparts to GW sources. The story, of course, always.
Varun, to save the bandwidth, maybe you can, the video can, yeah, audio is getting broken.
Gravitational waves, and no need to cover anything about your side.
Yeah. Maybe you want to go back to that first slide because your voice was broken quite a bit.
Okay. Yeah, I was just saying that sorry I couldn't be there in person. I was a bit unwell. I'm recovering now, but still not fit enough for travel. Am I audible better now? Your video is still on, and I don't know if that could be.
It's perfect. Yeah, we will switch off that video. Yeah, it's perfect.
Okay. So I'm going to talk about electromagnetic counterparts to gravitational wave sources. And the driving question, of course, is always what astrophysical inferences can we draw now that we have had detections and close to 100 of them? What all can we learn from what we are seeing? Okay, and in this case, a very important thing has been GW170817, where we had the first ever merger, direct detection of gravitational waves from a merger of two neutron stars. And that was accompanied with broadband electromagnetic radiation across the entire spectrum, going from radio, submillimeter, all the way to X-rays and gamma rays. And that led to an observing frenzy unlike anything that the world has seen ever before or since. There were about 1,000 different institutes involved in following up. Hundreds of telescopes actually participated in this. What you are seeing here. So the gravitational waves are telling us mainly about the masses and spins, geometric properties broadly, where the object is, how far it is, what's the inclination angle. The EM first step that comes in is getting the precise location of the object, but then we are also learning about ejecta properties and nucleosynthesis. So broadly speaking, the electromagnetic radiations are telling us about the surface of the object and what is happening there. Whereas what we are seeing with the gravitational waves has to do with the bulk mass distribution. So it is this together that is giving us the full astrophysical picture. So there have been a lot of things we have learned from 170817. Okay, as of today morning, it's close to 2,000 days since this event, and there are about 1,700 publications of this on ADS. And for at least for 4 years, there was more than a paper being published every day, with a total of thousands of authors having worked on this so far. So what are the key results? I won't go into the results today. I want to focus more on what came since. But from 1708-17, we had first direct evidence that short GRVs came from merger. We got proof from detailed follow-up observations that mergers, and these were enough to explain most, if not all, of the arc process elements that are found in the universe. It also gave us direct measurements of the neutron star equation of state, and it was an independent measure of the Hubble constant, which is going to improve with further detections. It was a great measurement of speed of gravity. We learned a lot about GRB jet physics. So there are a large number of applications, if I were to call them, across varied domains, a large number of things that we learned from a lot of different fields. Single event. After that, we had the third observing run, O3. And in O3, there were a large number of events detected as well. So what I'm going to show is a list of all events real time. And you see a lot of information here. If you see orange circles, it means it was likely a binary black hole. A big green circle means that the event was likely a neutron star merger. A lot of them got retracted over time as well. But in all of these events, you can see that neutron star black hole mergers and neutron star mergers, there were quite a few, order of a dozen. And people took this follow-up very seriously. There were a lot of searches that were done for counterparts to these events. There were about 1600 GCNs published on electromagnetic follow-up during O3. Here are a few examples just to show how extensively people searched for S190425C. About 8,000 square degrees was searched in optical using the Zwicky transient facility, and about 2,200 square degrees was searched in infrared. Then in S190426C, we followed up another event 200224CA, and this is the localization region. If you look at the close-up, each small dot that you see here is actually one pointing of Swift, and one where XRT took images to search for counterparts. And you can see that a lot of pointings were done. And despite all of this, nothing was actually found. The reason for that, I've listed out the neutron star events here. So what is shown with a brown background here is binary neutron star mergers, whereas rows with a white background are neutron star black hole merger candidates. And the two main numbers that you would have to care about here are the distances and the area in square degrees. So barring this one event, which is 1908-14 BV, most of the events were still localized to thousands of square degrees, and the distances were quite large. So the nearest event that we saw was at about 108 megaparsecs. For comparison, 1708-17 was actually at a distance of 40 megaparsecs. So that's a big discrepancy in the distance, and that has had huge implications for follow-up, because now what I can do is I can scale this to 1708-17. So without putting in any model physics at all, I say that all events were isotropically emitting the same amount of energy as 1708-17. And if that were true, then what is it that we would expect to see at Earth? So in optical, most surveys are sensitive currently to about 21st magnitude. And you can see that all of these would have been much fainter than that. In infrared, we can barely go to 18th or 19th magnitude, and these are much, much fainter than that as well. Similarly, in X-ray, the flux here is in terms of 10 raised to minus 8 ergs per square centimeter per second in the 10 to 1000 keV band. And you can see that maybe one event, which was the closest one, would have a flux of about 10 raised to minus 7, but everything else was much fainter. And for reference, the sensitivity of the current all-sky instruments is of the order of few times 10 raised to minus 7 in these units. So at face value, this is unsurprising that there was nothing that was absolutely seen in this, because all of these events were just that much further away. But what does that mean for us in terms of the big picture? What does it mean going forward? There are points that are important here, right? One is that although the nominal distances are large, there are also large error bars around those distances. So if you take this event, it was at 385 megaparsecs plus minus 164, which means that it could also have been at the closer end. And the searches that were done by the EM community were quite deep. So people did put in a lot of effort and did obtain, at least in some areas, highly sensitive images that could have found fainter counterparts as well. So all of this put together, can we actually learn something? And inspiration, of course, could come even from Sherlock Holmes. This is from the famous Silver Blaze story, where a detective says, "Is there any other point to which you wish to draw my attention?" And Holmes points out that the curious incident of the dog in the nighttime, where the dog did not bark despite there being a robbery. And Holmes points out that this lack of anything itself is curious. So we applied similar ideas here. So we said that, okay, with all of the searches that we have done with, say, the growth collaboration or the Zwicky transient facility, if we didn't see anything, what does that mean? So the orange curve here says that what is the probability of us not detecting as a function of absolute magnitude, not detecting anything if all events were at that magnitude. Okay, and there are a lot of different models that we have used here, but the bottom line is that 170817 was way too bright, and no more than 30 to 40% of events could have been as bright as 170817. Otherwise, we would have seen yet another counterpart. We also got other interesting results from O3. For example, based on what we have, uh, what we expect electromagnetic counterparts to be like in optical, and the fact that we didn't see anything, we also went back and looked at all of our archival data, saying what are kilonova-like false candidates, false alarms that we can actually get. And we found that there isn't much that can look like a kilonova. And based on all of this, we said that we can actually put an upper limit of about 900 mergers per cubic gigaparsec per year, which is this. And this is actually consistent with the LIGO estimates. If you take 170817, then this is the band. Okay, and GWTC2 did this. So it's just from electromagnetic observations now, we can actually start putting limits on the volumetric merger rates of binary neutron stars. So with all of this, what comes next? So O2 was done, and the glass was quite full there. We had just one neutron star event, but we had counterparts, and everyone was happy. We thought we will live happily ever after. Then came O3, and the glass was pretty much empty. Lot of neutron star candidates, no counterparts despite a lot of efforts. And it's not completely empty though, because we did get to learn some things. We did get to infer some properties about the counterparts by non-detections. And now that O4 is right on the horizon, what do we expect next? Well, if you want to look into that, then of course you can start gazing into a crystal ball. And there are multiple wavelengths in which we do follow-ups and searches. And in these, actually, the most common ones are optical and radio. Okay, in optical, we have currently Zwicky transient facility, which is a 42 square degree camera, which is leading the searches because of its being such wide field. There are, of course, other missions like GoTo and collaborations like Grandma, which are also doing a lot of work in optical. By late O4, there is possibility that LSST may have first light, and eventually LSST will dominate the game in optical. So things are well under control. The community has a lot of experience. And if not immediately, there's a good roadmap that has been set up, which means that we should be able to go much deeper. The Vera Rubin Observatory, or LSST, will be able to go to about 24th magnitude, making optical counterparts again accessible. Radio follow-up itself has continued for years for 170817 with UGMRT and JVLA and upcoming things ASCAP, SK, and so on. Again, the picture is quite clear. But a lot of interesting developments are actually happening in these other regions, in high energy, in UV, and in infrared. So let me quickly discuss some of those. So in infrared, there are two major new experiments that are coming up. First is an experiment coming up at Palomar called Winter. This is actually the graduate student working on this is Viraj Karambekar, who was an undergrad with me at IIT Bombay. This telescope is going to be able to survey large infrared, large parts of the sky in infrared. A similar project coming up in Siding Spring at Australia is the DREAMS project. And with these telescopes, we should be able to do wider and deeper infrared searches. The reason why this is important is that we have, based on improvement in models that are now consistent with 170817, we have concluded that there might actually be many scenarios in which case the optical depth of the ejecta is extremely high and all the radiation would come out primarily in infrared. Another advantage in infrared is that as opposed to say UV or optical bands where the light curve is continuously declining since the first hour itself, in infrared you actually have the possibility of the object becoming brighter for a couple of days before it fades out. So those are big advantages in terms of an infrared search. In space with UV, there are two ambitious missions as well. One is Ultrasat, which is an Israeli mission in collaboration with Germany. This will work in the 200 to 280 nanometer regime, and so pretty near infrared, but with 200 square degree field of view. And ultrasat will be able to catch, EMGW, of course, is just one of the science cases, but the early ultraviolet evolution of 170817, which was missed, satellites like this should be able to capture it. It is another important factor is that with coordinated efforts and surveys around the world, what we can get now is, unlike 170817, where it took 10 to 11 hours for the first discovery of the counterpart, it should be possible now to get it within an hour or so. And the early evolution is going to be extremely important to understand properties of the burst. The other mission is Dorado, an American mission with a 50 square degree field of view, working in far UV. So both these missions are something that we can look forward to in the near future. My own interest in this field lies in the high energy follow-up. And why high energy? Well, if you look at the time scale of this, then you expect X-ray and gamma ray radiation to come within seconds of the merger. UV is expected to peak in minutes, optical in hours, infrared, as I said, may continue to rise for a couple of days. Radio continued rising for many, many months after the event. Okay, so if you want the prompt detection, okay, the place where you will likely have the quickest confirmation that a counterpart even exists is in high energy. So that is something which I would like to draw your attention to next. What can we learn from high energy observation? Well, the first is that if you detect a counterpart, that tells you immediately that there is a neutron star involved. It could not have been two black holes. And that is quite important because there were a lot of ambiguous cases in O3. So if you take, say, GW 190426, the lighter component that you see here is clearly in the neutron star regime. But if you look at the heavier component, it could be a black hole, but it could have also been around 2.5 solar masses, which is kind of pushing it into the mass gap or even the neutron star territory. And then you look at other events like, say, GW 190814, you have an object which is quite well constrained at around 2.6 solar masses. Now, that is a problem region. We have not detected any neutron stars that are that heavy, nor have we detected any black holes that are that light. So if we had detected electromagnetic radiation from this event, we would have been sure that, yes, this was indeed a neutron star. Okay, and it gets even more interesting when you take this full classification, which is usually used by gravitational wave networks, where objects below 3 solar masses are called neutron stars, beyond 5 are called black holes, and this 3 to 5 neutron star region is usually called the mass gap. We don't know what objects should sit in the mass gap and whether they would emit EM radiation at all. And there have been several candidates during O3 which had at least one of their components lying in the mass gap. So if we detected EM radiation, that immediately tells us that, yes, there is a neutron star or there is some object which is not a black hole, which is doing this kind of emission. Having detected that, what can we learn from it? Well, the observables now, I'm not going back into what did we learn from 170817 and why is this important to do EM follow-up. I'm saying that if you detect only high energy radiation and nothing else, what can you learn from that? So the observables that you have are, you have the net luminosity of the burst, you have its spectrum, and you know its light curve, when did it peak, and what was the delay. Now, all of these depend strongly on how much ejecta was created, what was the tidal deformability of the components, was there a large cocoon which was formed, was there a shock breakout that was happening from the cocoon. And based on all of these, just by measuring these quantities, you can already start constraining emission physics, the shock breakout radius, what was the circummerger density apart from any disk wind that may have been created by the post-merger irradiation itself. If you detect a strong jet or not tells you an idea about the inclination. So all of these are things which you can infer from just the high energy radiation. Plus, all of this will be known within seconds from the burst. So you can then tell the rest of the EM community that, unlike the dozen events that all of us followed up with 1600 GCNs during O3, here is an event where we have already seen EM counterpart. So you can spend more effort on following up this source. tile as wide as you need to, go as deep as you need to, but there is a counterpart there waiting to be found. So that brings even more emphasis on high energy detectability. Looking back at 170817 for a second, Astrosat is great at detecting GRBs. We have detected more than 550 GRBs to date. When we looked at 170817, we didn't see anything. And the reason for this is this dark green region is the final LVC localization that was given for the event. And within this localization, if you look at the close-up, this is where the source was actually found. And this circle here demarcates the region of the sky that was unfortunately occulted by Earth as seen by Astrosat. So Astrosat orbits about 650 kilometers above the surface of Earth. And at that altitude, Earth blocks about 70% of the visible sky. So as a result, 30% which was lost, we just got unlucky. We did take the integral and Fermi spectrum, and we calculated that on the basis of that, we would have had a very clear about 10 sigma strong detection in Astrosat. So visibility would not have been a problem. But that teaches us an important lesson, which is that you have to be looking at the entire sky at all times. The other desi analog for this is if you try to call up anyone in their office, they're always out for tea. So you don't want to be out for tea when the event comes knocking. The next thing about 170817 was that the signal was extremely faint. So this is the famous figure that everyone has seen. This is the gravitational wave chirp, and you see that it peaks right around here. These are two Fermi light curves in two different energy ranges, 10 to 50 keV, 50 to 300 keV, and the burst is seen quite clearly. But this is the integral light curve, and you can see how faint this thing is over here. And in fact, the LSC paper with Fermi and integral, which talks about the discovery, explicitly acknowledges that if it was just about 30% fainter, which is just 15% further away, it would have been missed completely, which means that we have to be ready for fainter events. And this GRB seems to be a new class of burst completely. So what is plotted on this is the isotropic equivalent energy in high energy radiation going from 10 raised to 46 to 10 raised to 56 ergs as a function of redshift. And this blue dots that you see at the top are all long GRBs. Short GRBs tend to be slightly fainter, but this star down here is GRB 170817. So it was 3 or 4 orders of magnitude fainter than typical GRBs. It was broadband. It was seen from few keV to hundreds of keV, but it was also missed by a lot of missions. Some because of Earth occultation like Astrosat and Swift, and others because it was just too faint. Okay, now if this is so important, which are these other missions? Who all are the people who are keeping watch? These are the 5 satellites that currently dominate GRB discovery around the world. Okay, so Fermi and Swift are leaders by a large margin. They discover the most number of GRBs, followed by Integral, Astrosat, and GECAM, which is a Chinese mission. And Fermi and Integral saw this GRB, but Astrosat and Swift did not. In both cases, that was because it was occulted by the Earth. GECAM was not in orbit back in 2017. Okay, we can take this further. We can say that, okay, if you inject a whole bunch of 170817 like events at different points in the sky, what is the estimated flux as seen at Earth? Okay, so the green stars here are a simple model which assume that all events have exactly the same luminosity as 170817. Blue circles denote another model which is consistent with 170817 but allows events to be sometimes brighter, sometimes fainter, depending on the inclination angle. Okay, and you see this as a distance versus flux histogram. This turn off is simply because we stopped injecting events too far away. And this cutoff here is the Fermi flux limit. Okay, and you can see that we're barely able to sample the brightest tail of this distribution with a Fermi-like sensitivity. So the second conclusion is that given that these events seem to be rare and hard to find, you want an order of magnitude higher reach, maybe a order of magnitude better volumetric survey ability as compared to any previous mission. And then the last point is that you did see something, so what? So this is an excerpt from the paper, the discovery paper. The power law index was not well constrained. It is 0.14 plus minus 0.59. You can see that the error bar on alpha is larger than the value of alpha itself. The tail emission could not be measured, but it appeared soft. And overall, it says that the emission is too weak and it is not possible to rule out a non-thermal spectrum and so on. So if you want to actually characterize it rather than just detect it, then you need to have a wide spectral band. You don't want to just say it exists. You want to be able to make scientific inferences from the existence of that thing. Okay, so these are the requirements for a next generation mission if you want to actually detect and study these electromagnetic counterparts to gravitational wave sources. You need an order of magnitude higher reach or grasp, which you can attain by having a large area of your satellite, have lower background noise, do better background rejection. You want to cover the entire high energy range, going from a KeV to beyond an MeV. And to get continuous all sky coverage from low Earth orbit, you need two satellites placed on opposite sides of the Earth. So with all of these goals in mind, we proposed a very ambitious mission called Daksha. Most of you may have heard about it, hopefully, by this point. So Daksha is a pair of satellites in low Earth orbit, and the satellites comprise of three types of detectors. The workhorse are 17 sets of medium energy detector packages. These have been used in many space missions before, and they give coverage from 20 to 200 keV. And they are complemented with these low energy silicon drift detectors and high energy scintillators, which give a total coverage, all three combined, going from 1 keV to beyond an MeV. So what will Daksha gain? Daksha, the two satellites together have a median all sky effective area of about 1700 square centimeters. Uh, in comparison, say Fermi has something like 300 square centimeters. The sky coverage is 100% with both satellites put together. The sensitivity is comparable to Swift-BAT, but Swift-BAT covers only about 11% of the sky. And the energy range covered is much higher than either of the satellites. In particular, we do extend down to 1 keV, which is very important if you want to detect any kind of absorption components in the radiation or any kind of thermal components in the radiation. With all of these capabilities, what can Daksha do? Based on what model? Just a moment. Yeah. Based on what model you believe in, the rates change slightly, but we expect to detect dozens of binary neutron star mergers per year, and also about 550 on-axis GRBs. That's about 50 short GRBs and 500 long GRBs per year. On board, we can localize it to about 10 degrees, which is great because in a few pointings, a telescope like ZTF can cover that entire area. With on-ground processing, the localization is expected to improve. Of course, if the burst is brighter, we will do much better localization. It is the only mission that will be able to give the broadband spectrum that includes soft spectrum. So for GRBs or for any other high energy burst, typically what happens with a mission like Swift is that the satellite has to slew and point its soft X-ray telescope to that location for getting more detailed soft spectra. But Daksha will actually have open all-sky detectors for that as well. It has excellent capabilities for hard X-ray polarimetry. And then another fun thing is Daksha will allow us to look under the rug. So if you look at the LVK sensitivities, the threshold for what is considered as a gravitational wave detection is set by all sky all the time false alarm rate. But if you have an electromagnetic detection, then it gives you the direction of the source and it gives you the time window in which the merger must have happened. That allows you to significantly reduce your threshold because it lowers your false alarm rate. You have to find any event that you find in GW data has to be consistent with this. And we did a bit of estimation on this, and it will allow us to almost double the binary neutron star detection rate with gravitational wave networks. And in general, this opens up a huge discovery space, especially with these subthreshold sources, but also more broadly with the reduced false alarm, with the increased sensitivity itself, it gives us a huge leap. I will, so there's a question in the chat, what will be the sensitivity compared to other telescopes? I'll come to that in just a bit. So what other missions are out there right now? The new missions which are coming up are Swarm and GECAM. So Swarm is a French-Chinese mission, which is expected to be launched this year sometime. And GECAM, they already launched GECAM A and B. One of them failed, the other works. They have launched GECAM C, which is a lower sensitivity thing. So China is launching satellite after satellite in order to cover this. Conceptually, GECAM is very similar to Daksha, but sensitivity wise, it is lower. There are also a large number of CubeSat teams. So here are a few. There are some concepts, some have been launched. So GRB Alpha, Camelot, Burst Cube have already been launched. Hermes Pathfinder has been launched. But all of these are much lower sensitive area. And the goal in these missions is that you launch dozens or maybe even hundreds of such small satellites. So for those unfamiliar with the jargon, CubeSat is typically a 1U unit is something like this. So this is a cube which is 10 centimeters on a side. So this would be a 6U unit, which is 10 by 20 by 30 centimeters. So they have very limited sensitivity. Okay, so here is the slide I promised comparing these different missions. So I have not put COMTEL here, but here are effective area plots of various missions. Let me see if I can just zoom in here to show this a bit better. Sorry, I can just zoom it like this to show you this plot better. Okay, so this is 1 MeV, and this is the Daksha high energy detector sensitivity. For comparison, this is the sodium iodide detectors of Fermi. This is the Swarm gamma ray monitor, and this here is the Fermi BGO detectors. So the sensitivity is about a factor of 2 higher as compared to any of those. So I hope that answers your question. And this table here shows a comparison of a bunch of missions, including Theseus, which unfortunately has been cancelled already. But also it has Swarm, Eclairs, Fermi, Swift, and GECAM. So different parameters are given here, but what I'd like to draw your attention to is this volumetric, how much volume can we probe for, say, 170817 like events. And you can see that Daksha does a much better job than anything else. So it's about a factor of 13 better than Swift BAT and about a factor of 5 or 6 better than Fermi GBM in terms of how many 170817 like events we can detect. Okay, so that is a big advantage in favor of this mission. I would take a small detour here to address what else can Daksha do. So what are our broader science goals? If you want to go into details, just scan this QR code or note down these archive numbers. This is where we have discussed the mission specs and the science case in detail. There are also more papers that will be coming up soon. The polarization paper we expect to submit by the end of this month. But let me give you at a glance version of this. This slide is too dense, so let me spread it out instead. So we have a large variety of science cases that we want to address with this mission. Relativistic transients is the first one. We have already been talking about electromagnetic counterparts to gravitational wave sources, where we have the highest sensitivity among all satellites. But for GRB studies in general, this is the only satellite that will give soft prompt emission. And also, thanks to the very high sensitivity, while detecting faint GRBs is fun, we can do great science by doing time-resolved spectroscopy of the brighter GRBs. And that is because with so much sensitivity, we can break our data into small time segment bins. And that will still give us enough SNR to do spectroscopy. So instead of fitting an averaged function for the entire spectrum, we can now start seeing how spectral parameters actually varied with time. In terms of GRB polarization, the current record holders are AstroSat CZTI and Polar. And the GRB polarization abilities for Daksha are better than any of these missions. Then the next set of science cases is to deal with compact objects in general, where we could be studying SGRs and magnetar flares, searching for high energy counterparts to FRBs. As you all know, there is a large uncertainty over what exactly FRB emission sources are, and there are several models which do predict high energy emission. We will be able to monitor accreting X-ray pulsars. So Fermi GBM has been doing a great job at this. and we have much higher sensitivity. So we did simulations and we found that any source that Fermi can detect, Daksha can detect it extremely easily. We can also study various other elements. So Earth Sun system, quite cool result is that there is gamma ray radiation that is associated with lightning, and these are called terrestrial gamma ray flashes. There have been a few dedicated missions that have been launched to study these TGFs, but Daksha actually has higher sensitivity than even those dedicated missions for detecting such things. We will be able to do solar flare studies, and even monitoring the Earth's atmosphere and atmospheric response to space weather is something that can be followed up. When you have a high sensitivity mission, other interesting science cases pop up too. Surud found an interesting case where by studying GRBs that are detected jointly by both satellites, we can look for signs of microlensing and actually use that to probe primordial black holes, low mass primordial black holes, and probe or possibly rule out a phase space that hasn't been probed by other missions so far. We can also study persistent sources with Earth occultation, novae and other slow transients, and so on. What's the overall status? Daksha is being built with IIT Bombay as the lead, but jointly with a lot of other institutes involved, PRL, TIFR, Ayuka, RRI, ISRO, and the science team is spread over even more institutes. And we actually have a proof of concept ready. So this is our detector board. It's populated, tested, working. We have actually labs in IIT, TIFR, and PRL at all places. We are working copies of this board. So we are about to submit a closure report to ISRO. So ISRO had given us seed funding to show that this is actually feasible, and that part is now accomplished. So on the basis of that, we can go ahead and now tell them that this is ready, and ISRO will now evaluate the full mission for approval. And I will close with that. So if you want to know more about Daksha, go to this website. Oh, I just looked at the clock and realized that I've been speaking too fast. So I'm done well ahead of time, on only 40 minutes instead of 50. I hope that's okay, Gopal.
Oh, that's perfect. We will have questions, so and that will be great. Yeah. Okay. Let's give a big round of applause to Varun for this amazing mission. So, questions, comments from younger colleagues. Yeah, and also Zoom, there are a few. Varun, can you answer to the questions in the chat straight away?
I see only one question in the chat.
Okay.
From Ramiz Muhammad, which I answered when I showed that plot. I
Okay.
don't see any other questions in the Zoom chat.
Sure. Okay, so then, yeah, Avinash.
Hi, I have a question regarding pulsar timing array with the gamma ray millisecond pulsars. So there has been recently one paper by Fermi. So can Daksha also we can do a similar thing with better sensitivity?
So the timing resolution of Daksha is a microsecond, and we will be able to get absolute timing accuracy of about a millisecond. Should be quite straightforward to get. What I understand is that the pulsars that Fermi is talking about are actually emitting in MEV to GeV range, whereas in our sensitivity range they are much fainter. So that is why we will be able to see fewer of those sources. That said, there is nothing, we haven't explored this in great detail, and there is nothing preventing us from doing that. So, if you or anyone else here is interested in probing it, then I'll be happy to work with you to figure out what our sensitivity is and what can be done on that front.
Okay, thank you.
I think there were a few other questions. I saw somebody raising. No. Okay. Yeah, then Sriram.
Thank you. Hi, Varun. Thank you for a wonderful talk. I had three questions. You talked about GW190814, and you talked about the masses being 2.6 solar masses and 23.2 solar masses. You couldn't see it in the optical because they were too far away. The same arguments applied as you.
Probably too far away, yes. So if you let me go back to this slide with all the listing. So this is the event, right? 190814 BV. And you can see that the distance, this is the third column here, and the distance is 6 times higher. So the median distance itself. Okay, so the flux is going to be 36 times lower. That's about 3 or 4 magnitudes fainter than 170817. The area was small. We did search to much deeper limits than 170817, and we didn't find anything, unfortunately.
Okay, I understand. A completely different question. You talked about high energy observations. Do they
Yes.
allow you to localize the source in the sky easily?
Yes, so we can localize typically to about, so with the Daksha, we localize to about 10 degrees for a faint source. As the source becomes brighter, it is just inversely proportional to flux. So if you take a typical GR beat that is detected by, say, Fermi today, we can localize that to a degree probably.
Okay.
And 10 degrees radius is few hundred square degrees area. That sounds like a lot, but with wide field ground based, see, once we know that, right now, here's the problem. If you look at, say, O4 predictions, we are looking at probably few candidates per week. Now, to follow up one sky area of, say, 1,000 square degrees, I have to spend an entire night of a telescope on it. So if you want EM collaborations to follow these up in great detail, you are talking of essentially shutting shop and doing only this full time. And of course, that's not going to happen. Now, on the other hand, if we see electromagnetic radiation, and then we go to these telescopes and say, look, this is not a black hole merger, right? This emitted photons, we know this is there. Then you can afford to make a stronger case and spend more time and effort in following up. And then tiling a few hundred square degrees is quite achievable with current technology.
Okay. And the last question related to, Surhut's proposal for observing primordial black holes using microlensing. What mass range are we talking about?
If I remember correctly, this is 10 raised to minus 11 to minus 14 Earth masses. But I might be butchering that badly enough that Surun might want to strangle me. What I can tell you instead is Surun has a grad student working on this, and she's written up a paper which should get submitted soon. So let me get back. Actually, wait, I can do better than that. Since we have the luxury of having some time, let me tell you exactly what we can do. Yes, so 10 raised to minus 11 to minus 16 solar masses, which is pretty much not probed so far. The interesting thing here is that the size scale of this is smaller than optical wavelengths. So you can't study these with optical light at all. You need high energy radiation to be able to probe these range.
Okay, I understand. Thank you. Thank you.
Coming back to your second question, by the way, there is one more part. The localization that I've been talking about is a single satellite localization, which is what it will happen for the majority of the events. If we have a detection with 2 satellites, okay, a part of the sky, the satellite. So if I have Earth here and one satellite here, one here, then this mid plane is visible to both satellites, right? This part is hidden for this one, this part is hidden. So about 30% of the events will be detected by both. And there we can actually now triangulate. We can use the same LIGO-like idea of the delta T between the 2 satellites to get a narrow arc. Now there is another proposed NASA mission called Moonbeam, which is a slightly lower sensitivity, factor of 2 actually, lower sensitivity in the Daksha, but they are going to go into a highly elliptical orbit, up to 1.3 times the distance to the moon. So we are taking up a joint study with them, saying that if Moonbeam plus Daksha or Moonbeam plus both Daksha detect an event, how well can we localize that? And that should easily come to a sub-degree field of view. When a telescope like, say, the Growth India telescope can easily observe that area and just look for counterparts.
I understand.
So,
thank you, Varun.
Welcome.
Hi, so I have a very naive question. So when you are saying that the high energy detection actually favors neutron star, that is why it is so.
Because there were photons, you can't have it with black holes.
Okay, okay. So immediately we can actually predict the surface magnetic field or so?
No. It's simply that, okay, so there are ways in which black hole mergers can cause some electromagnetic counterparts. They typically come from scenarios like having a black hole merger in the disk of an AGN, where the merger disrupts the gas in the disk, and that gives rise to optical flaring or something like that. So this happens at lower energies and at longer time scales. So if you have, we do not have any theoretical way of having black hole mergers generate any X-ray or gamma ray emission at short time scales.
Okay.
So if you have X-ray gamma ray emission at all, then it means that it has to have been emitted by a neutron star. It does not directly depend on the magnetic field. There are indirect implications. I'm not sure if they will be observable, strong enough to be observable.
Okay. And your slide number 10, the mass gap you have shown.
Yeah.
So all those purple compact objects are like, what are they?
Okay,
Purple.
so okay, I jumped through this figure as I was speeding through my entire talk. For if you take any event, let's say this event which was actually retracted, then on this gray line you see two blobs here. So the size of this circles is telling you the probability that this was a binary neutron star event versus a terrestrial event. Okay, so if you take something which is, say, this one, okay, I'm pointing out to retracted events because it's just easier to follow with that gray line. Then this was classified as a mass gap event, which meant that at least one of the objects in it was between 3 to 5 solar masses.
Okay.
If both were above 5, it was called, so the classification used by LIGO is was on one of my slides. Let me jump out and look for it. Where did that go? Here, right? So below 3 solar masses is a neutron star, 3 to 5 solar masses is mass gap, and above 5 is black hole. The reason for this is if you look at all the black hole masses that have been measured with, say, X-ray studies and stuff so on, we have never found a black hole that is lower than about 5 solar masses. Error bars extend downward. Okay. We don't have a fundamental physics reason as to why you cannot have something like a 3.5 solar mass black hole, or for that matter, a 10 raised to minus 11 solar mass black hole. Okay, but the fact remains that observationally, we haven't seen black holes in this range. Observationally, the heaviest neutron star is actually sitting here at 2.1 solar masses. But there we are theoretically saying that, okay, up to 3 solar masses, depending on equation of state, we can have a neutron star. But this region, we have not seen compact objects in this region observationally at all. So there might be an astrophysical reason. For example, if you have to form a heavier black hole, then it may have effects on the way your supernova explodes, and it may actually cause more fallback, resulting in black holes always getting, so if you have a certain type of supernova explosion, you leave behind a neutron star. Maybe if you go into a territory which is large enough where the core was heavy enough to make a black hole, you also get more fallback. So that instead of that black hole being just above the neutron star black hole boundary, it ends up becoming much heavier. So there is plausibly a astrophysical reason here, but it is just observationally empty space, and that's why it's called the mass gap region.
So here, this 2.59, we are calling it neutron star?
No, this is mass gap.
Okay. That's
sorry, no. This is neutron star. This is neutron star. Yes. This is probing out into the mass.
It is neutron star?
No. Sorry?
Okay, that's my question. Okay.
No. So there is no confirmation that that's actually a neutron star. It's the chirp mass is much more accurately determined. The mass ratio is a problem, even though it's unequal mass. So then that's the error bar issues walking in. Varun, thank you very much for a fantastic talk. I have a bunch of questions. Is that all right?
Yeah, of course.
So, I've been a bit confused. You in one of your slides, you said 170817 is actually a bright event, even though we know the fluence is much lower. So in what sense did you say it's a very bright event? I'm a bit confused.
Okay, so if all events had the same optical emission, as 17017. Okay, so what we did was that we used a tool called sim survey. Okay, I'll give you a little bit of behind the scenes. So we have a package in which we can inject kilonovae with various models into the sky, and then we simulate our observation strategies and say, would we have found a counterpart? Okay, and so you take, say, one of the events from O3, you take its localization volume, you throw in thousands of sources of kilonovae, and you say you tile it as ZTF actually observed that area, and you say, okay, these fraction of them were found and these were the ones not found. Okay, and based on the fact that despite doing detailed follow-ups for about a dozen or so events, we didn't see anything, it allows us to put constraints on kilonova models.
Right.
So one of the models we took said that every source was exactly the same as 170817. So 170817 had a peak absolute magnitude of about -16 or something like that. And if that was the case, then what would have happened? And the answer is that we should have detected something. So clearly all cannot have been the same absolute magnitude as 170817.
Okay, thank you. So this is the kind of a follow-up comment on that. So some of my colleagues in Seoul National University, they are trying to come up with something called 7DT. I kind of briefly mentioned this to you, if I'm not mistaken. So what they're trying to do is that they're going to have a spectral survey in 3 days. It's kind of a it's not a, it's essentially optical wavelength, but a narrow band. So that should be, they are exclusively searching for kilonovae, and combined with this will have important implication, right? I mean,
yes,
irrespective of whether you see it in LIGO or not.
right.
So,
Yes.
so this is something maybe you guys should talk to each
So
other.
that is the other thing which was done here. So this second paper, what we did was that independent of LIGO, we said that here is what we think overall theoretically kilonovae should evolve as a function of time. And then we went back and looked at all of our data, saying how many such candidates have we ever seen? And right now I think we found one. We're
Yes.
not strong enough to claim it a kilonova, but we couldn't rule it out either. And on the basis of that, we then put an upper limit, saying that if kilonovae do this, then how many neutron star mergers could there be in space? So that was kind of work done on that front.
Okay.
Without relying on GWs.
Okay. And I have there was something I was noting it down. Give me a second. Oh, Shantanu.
But you can ask quickly.
I have to go back to it.
Okay. So if you ask the question in where GW17087 has not been seen, okay, which wavelength bands, okay, so I can think of two. You can correct me if I'm wrong. It has not been seen at millimeter waves. It has not been seen in TV gamma rays. So now obviously this GRB was very far away, so probably it wouldn't have been seen in TV gamma rays.
So TV, I know it was not seen. I'm not very sure about millimeter waves. I know it was detected in sub-mm. I know it was detected in centimeter waves. So if it was not detected in millimeters, it might just have been because people didn't bother.
Gigahertz. I'm talking about gigahertz.
Gigahertz detection was
But what are detections?
Yeah. Lot of JVLA detections. In fact,
JVLA
one of the
still, I think-
postdocs said, yeah, JVLA goes down to gigahertz.
Yeah. Okay. Okay. So anyhow, so what are the prospects for detecting TV gamma ray counterparts and in the
I
near
would
future?
personally, I wouldn't bet on it. And that is because even if you look at just GRBs themselves, right, with a few thousand GRBs known to date, we have one or maybe two detected in TeVs. So you need to be incredibly close and incredibly bright to get TeV emission. Another problem that comes in at high energies in general is that first is that it is hard to create high energy photons. And second is each photon carries so much energy that for a given flux level, you get extremely few photons. They're very related, but not quite the same factors. So as a result, you are going to get extremely few photons per square centimeter on Earth from any of these events. And that makes it rather unlikely to be detected in those energies. That is also part of the reason why Daksha sensitivity, we don't bother too much beyond an MeV. Unlike Fermi, which was meant to be also a gamma ray space telescope for studying steady sources, here our focus is just on the transients, and it's hard to get GeV transient emission from a lot of GRBs. They're obtained for a few, of course. TeV, it's not, GeV is not as bad a scenario as TeV is, but for search, the KeV to MeV range seems to be the best.
Okay. Yeah, I mean, so just a follow up of that, you mentioned about that prompt emission and the soft spectra, the possibility, right? That will be that will be fairly unique, right? I haven't even many of the soft gamma ray bursts, right? Where short hard gamma ray bursts, where they have suspected the kilonova and all that, right? With X-ray. So those are fairly uncertain, but
Yes.
your statement is that this will be, you'll have several.
So I can give several examples here. 17017 itself, there are hints of there being a soft thermal component in the prompt emission, but Fermi sensitivity cuts off at 8 keV, so it's not quite enough to measure that. With classical GRBs, there have been studies which indicate that there could be a soft break in the spectrum, and it's modeled only as a break because no mission has sensitivity enough in those energy ranges to actually be able to fit it. If you look at the band spectrum itself, which is the typical model used to fit GRB spectra, there have been some studies which show that if you actually do time resolved, then you can start fitting more spectral models, more detailed physical models, and the average of them over time ends up looking like a band spectrum.
Okay.
So being able to detect those in prompt emission is going to be quite important. From a kilonova perspective, the kilonova strictly is the optical IR emission from this, but from a neutron star merger perspective, another thing which is important is that the most plausible thing right now is that there is some sort of a cocoon being formed, and there's a shock created inside that which is breaking out, followed possibly by a structured jet and so on. So when you see the shock breakout, there's still going to be some optical depth beyond it. And it is possible, not very likely, but just possible that you could actually even constrain the NH column density by doing soft X-ray spectral measurements. So that's another interesting prospect. So you'll be able to measure exactly where you start seeing the X-ray gamma ray photons from the source.
Yeah, that will be amazing, especially, but there are doubts about the cocoon scenario, right? But it doesn't matter.
There are doubts about whether the full-fledged cocoon as such exists, but the big picture model, if you look at it, the fact that material has to be ejected, has to form some kind of a cloud, and that's why I said possibly a structured jet, possibly a cocoon, but then the final, the cloud is forming before the impact, if you want to call it, and the impact is what is creating a shock. And then you are seeing a shock emission, possibly a shock breakout and everything, right? That's how you explain the delay between 17017 and the gamma rays. So that part is not really in doubt.
Yeah, precisely. Maybe eventually, very careful those things. Whether you can actually argue whether there's a black hole formed or not, eventually. That'd be an interesting thing to think about too.
Yes. Yes.
So, further, any more questions? Yeah, go ahead.
Okay. So I have a question. You have showed various what is the expected magnitude in optical and other bands for some of the gravitational wave detections, right? So how does it vary with the inclination angle?
So this is a ultra simplistic model. Okay, just for showing comparison, we assume that everything is isotropic and same as 17070.
Okay.
So this is extremely simplified. If you want to do a more detailed thing, then here is one example of it. This one. Okay, so the green line here is my ultra simplistic model. Everything is exactly 17070. When I start throwing in inclination, for example, then this is a cocoon model, but there is another paper in prep actually where we are probing this for a variety of structured jet models. So in high energy, the variation is sometimes modeled as a Gaussian jet with a certain sigma, which is few degrees, or as a power law fall off as a function of angle. In optical, the variation is not quite as high. It is within an order of magnitude. In X-rays, gamma rays, it can be a few orders of magnitude from the peak jet to outside. And also, depending on whether you are seeing on this thing as a polar or a equatorial aligned merger, that also changes the nature of the kilonova. In the equatorial region, you get what is called a red kilonova because you have more ejecta in the equatorial plane. So radiation is getting absorbed, reprocessed, and re-emitted at longer wavelengths. Whereas if you are looking at it along the polar angles, then there was less ejecta to begin with, and the jet created by the merger will also plow out a path for you. So the net combination is that you will actually see bluer emission on the polar sides.
Okay. Sorry, I just forgot. Yeah. Okay. So there are cosmic accelerations, right? So can the neutron star mergers be one of the source of those?
Possibly. I don't think they're believed to be a major source, but I'm sure they could be a source. I'm not sure.
From the gravitational wave, what do you say? From the template itself, can we say what might be the inclination angle, or do we need some additional?
So there is quite some. So you can measure angle from the gravitational wave signal, but there is quite a bit of degeneracy there. And electromagnetic observations can actually help better rule that out. And also, if I remember correctly, getting the distance which you can get from electromagnetic measurements, that also helps in breaking a bunch of these degeneracies within GW data.
Yeah, I mean, especially black hole neutron star, because they are unequal masses, the higher modes are possible. So that actually kind of feeds back onto the inclination again. So that's the reason one of those events are much better localized, because they could get the higher, not just the the
Okay.
droplet. So you go beyond that unequal mass. And so the inclination also comes to help because additionally, yes. This one more question. So
it's a very broad question. Because we have such a small sample size, especially with the GW and EM counterparts at once, how are you dealing with this not being like a biased selection of sources? Because we are planning various missions, we are planning EM counterparts in the future. How are we sure that this is not a very small sample size? We're looking for the nature might be doing other things which we might not have seen.
So that's a great question. The first answer is we are astronomers, so we always work with one data point. But a more serious version of it is that no, we are actually being aware of this. So, for example, this other work that I talked about, which is something in prep, let me give you a glimpse of it. If I have a slide here. Yeah. So here, what I've done is I've considered 8 different models from different groups, which account for 8 different models of emission from neutron star mergers. Okay, all of these have been scaled to allow 170817. So they are all consistent. And then we have done our rate calculations on the basis of all of that. So if all events are isotropic and have the same energy as GW 170817, then Daksha will detect 3 per year. But if you have this Gaussian Phong model, then we will detect 12 per year. If we have an optimistic cocoon model, we will detect 18 per year. Okay, so we are taking that into account in this way by accounting for theoretical variations. But then we also did things like this, where we tried to be agnostic about it. We took a lot of models saying, here is a model assuming Kazan's model, there is Matiabula's models. So a lot of these models were made by different groups, and those assumptions are being folded in. The last thing is that bias is not necessarily only towards optimism, it could also end up being towards pessimism. So for example, one of the things we are working on right now is if you take black hole mergers, 150914, the first ever detection actually had a weak 2.7 sigma candidate in Fermi. Okay, saying that there are potentially gamma rays, and there was it was a big party with people publishing papers as to how the black hole merger could have emitted gamma rays and so on around that time. But so we don't really think that they'll emit gamma rays, but the cost of searching is so low that right now one of my PhD students is doing a full search over all of AstroSat archival data corresponding to every single GW trigger ever received, saying that did we see anything? And based on that, we are putting constraints on luminosity functions of black holes. So we do try to be aware of potential biases to the extent that we can. And that is also when proposing a mission, for example, we don't propose it. EMGW could be the main science case, but we don't propose it unless we have a lot of other guaranteed science as such. All the GRB science is guaranteed because we have detected thousands of them. We know what all is going to happen and how we will do better.
Yeah, that's amazing answer. Thank you. But I just want to add to that, when the LIGO was funded, it was based on essentially 3 neutron star binaries. And we know that one of them will merge in, kind of 50 million years time or something like that. So yeah, so the payoff was pretty good. So yeah. Okay, so thank you very much for a wonderful talk. And yeah, we overshoot time. So that's perfectly all right. Thanks again. Hope to see you soon.
Thanks a lot. And I apologize again for not being able to come in person. I wish I were there.